All right. We're now going to address the topic of magnetic fields. Okay. And to start, it was noticed, okay, sometime in the late 1800s that when you have things like cathode rays, and at the time they didn't know what cathode rays were, okay? All they knew is that there were beams that could be emitted from what they called cathodes and anodes, which are basically positive and negatively charged plates. And these beams, one of the properties of these beams is that they would be influenced by magnetic fields. If you brought a magnet in their presence, the beams would deflect. Okay? And once it was understood what the cathode and anode rays were, that they were actually beams of charged particles, then it became a question of why are charges influenced by these magnetic fields. Now, certain things occurred when they would observe this phenomenon. The beams would always be bent perpendicularly to the magnetic fields. And if the magnetic fields were along the path of the beam, there would be no deflection. And so that meant that there had to be some weird influence, for lack of a better phrase, that the magnetic fields exerted on the beams. Now, this is another issue of we have an explanation for how something works, but not why. Okay? The first law that we're going to write down is known to be written like this. Okay? And what this equation is telling you is that if you have a charged particle Q in the presence of a magnetic field B, now don't ask me why we use B for magnetic field when we use E for electric field, F for force, M for mass, V for velocity. Probably for the same reason we use Q as charge, even though Q has nothing to do with charge. B has nothing to do with the magnetic field, although we just simply define the magnetic field as B. But this is known as the Lorentz force, right? And so what this implies, this is the cross product, okay? So this is a vector operation, and if we denote our magnetic fields, let's say the magnetic fields are blue, okay? So if I have downward acting magnetic fields, okay, and I inject, let's use red for the charge, and if it comes up, there we go. So if we use red for the charge, oh, it didn't take it. I don't know why. Let's try this again. There, it took it. So, we have a charged particle Q, and it's being injected into the magnetic field like this. And if we draw a coordinate system, okay, we have to, since this is a vector operation. Let's draw our coordinate system like this. And we'll assume for the moment that our particle is positively charged. Okay, so the right-hand rule, right? If you recall from 298, we have the right-hand rule, which it would be very difficult to draw on a two-dimensional sheet like this, but it says if you take your index finger and point that in the direction of your first vector in the cross product, so index finger, and then your middle finger is in the direction of B, or your second vector, then your thumb naturally points in the direction of F. And this is for the right hand. Do this with your right hand. That is the force on a positive charge. Okay, that would be the force on a positive charge. So, what that means is, what that gives us is, if we do this, then my index finger would be pointed to the right, my middle finger would be pointed down, and my thumb would be pointed into the screen. Okay, so my thumb is going to be pointed into the screen. Now, how do we denote that, since we actually have to work in 3 dimensions here? So, first things first, what direction is that? So, into the screen is actually your negative z-axis, okay? So our coordinate system actually now looks like this. So I can imagine plus z coming out of the screen, negative z going into the screen. And we denote vectors on a diagram like this. Okay. We're going to denote circles with a dot are coming out of the screen. And X's represent vectors going into the screen. Okay. So with that in mind, what's going to happen is that once the charge reaches, actually let's bring it back to the red first. Once the charge reaches the point where the magnetic field is established, it will experience a deflection into the screen. Okay? Its deflection will be into the screen. So it would have a deflection into the screen. And if I were to look at this from above, okay, if I were to look at this from above, it didn't take it. So from above, okay, what we would see is the magnetic field going into the screen, and so we would see the magnetic field like this. And if we imagine the charge being injected, now the charge from above is still going to be traveling to the right in our picture here. And so my charge is initially pointed this direction. And in this case, if I do the right hand rule, this is going to be deflected upward. So the path of the particle is going to be something like this. Okay? And the deflection, the strength of the deflection is going to depend on A, the strength of the magnetic field, and B, how wide a region it is. If it's a very narrow region, then the deflection might not be a lot. But as the particle gets deflected, if it keeps experiencing the field, for example, what I mean is if the field were like this, where it were just in a thin column like we have here, the deflection might not be very much. But if it were very wide, so that as the particle is deflected, it would still keep feeling the field, then the deflection would be even stronger. If the field is large enough, then you might be able to see what's going to be happening. The charge, if the field is strong enough, the charge is simply going to be deflected in a circle. Okay, if the field is wide enough, then this deflection would just make a circle, and the charge would just keep moving in that circle. And this is actually the basis for certain initial technologies that started the particle accelerator revolution. So certain devices like the cyclotron, okay, operate on this principle that the charged particle, whether it's an electron or a proton, will experience a force in a constant magnetic field. If it was injected at a right angle to that field, it will move in a circular form. Now, its speed will not change. Okay, the magnetic field will not change its speed, or it won't change the particle's speed. Let me be clear, but it will continually change the direction. Okay, now. A couple of things, and these are some mathematical notes. The cross product, okay? Oh, and by the way, before I get into the math, let me state that when you have a negatively charged particle, you do the right-hand rule, but then reverse the result. So if this were a negatively charged particle, we would experience downward deflection, and the negatively charged particle would go like this. So the right-hand rule applies for positively charged particles, and opposite for negative charge particles. Okay, so just note that. All right, so first things first, the cross product. Let's look at some math notes. Okay, so first things first, V cross B can be written as the absolute value of V and B times the sine of the angle between them. Okay, and if the angle between them, as in this case, if the angle is a right angle, then this just goes to VB, right? But when you don't have a right angle, Oh, and if the angles are parallel or anti-parallel, then the sine of theta just goes to 0 and the whole thing goes away, right? So this is when theta equals 90, and it equals 0 when theta equals 0. Okay? All right. Next thing, if you remember V cross B, if you don't have a right angle, right, then you can still use this form. Okay? You can still use this form. However, if V and B are given to you in component form, okay, so there's usually two types of ways this problem can go. Number one, you might be given something like a particle enters with a velocity equal to x meters per second at an angle of 30 degrees to B, okay? You might be given something like that. Or, number two, you can be given V is equal to x in the I direction plus y in the j direction plus z in the k direction, and B is equal to bx in the I direction plus bx y in the j direction plus bz in the k direction, and you would be asked, what is V cross B? Okay? When you're given the problem in component form, right, if you have the velocity components and if you have the magnetic field components and you want to know V cross B, then what you do is the matrix, right? So you would take, and I'll tell you what, let's label these, well, we'll use x, y, and z. Note that I'm denoting these as velocities rather than positions. So technically I really should have used Vx, Vy, Vz. But for the sake of example, we'll leave it as is. So your V cross B can be written as the components of V and then the components of B and then you find the determinant of this matrix. Okay, so the determinant of this matrix is going to be your velocity in the y direction times the z component of B, and the z component of the velocity times the y component of B in the I direction. And then it goes minus xbz minus zbx in the j direction, and then plus. So remember, when you have multiple or essentially more than a 2 by 2 matrix, when you have more than a 2 by 2 matrix and you're going through the individual determinants, it goes plus minus plus minus plus minus as you're adding extra terms. So that's where this minus sign comes from, just as a reminder. And then this would be xby minus ybx in the k direction. Okay? So there's your determinant. And the components of all of this represent your coefficients in front of your, or I should say the magnitude of the component of V cross B in each direction. Okay. And then when you have all of that, you just multiply by your charge, and that will give you the magnitude of the force. And then the right-hand rule rules for the positive and negatively charged particles give you the direction. Okay? So let's look at an example here. So, for example, what if we have a proton entering a magnetic field so I've got a magnetic field, and we'll put the magnetic field constant in the downward direction, and we'll give this a component of 0.5, and the units on the magnetic field are the Tesla, and we will define the Tesla here in just a little bit. But for the moment, just understand that the units on the magnetic field are Teslas. And we're going to, this is going to be in the negative K direction, okay? And if I inject a particle, let's say a proton, so Q is going to be 1.6 times 10 to the negative 19 coulombs, and let's give it an initial velocity of 4 times 10 to the 5th meters per second. Okay, and we'll put this in the I direction. Okay, so formally what we're doing is giving a coordinate system just like we had just now. Okay, so there's our coordinate system. And so what I want to know is this, okay? I want to work out in the value of the force on this particle and its direction using both forms that we have. So first things first, let's use F is equal to QVB sine theta. Okay. So when you take the absolute values of V and B, this is what you get, right? And then B, let's actually do the cross product. And we'll show explicitly that these two expressions agree. Okay? So for part A, here we go. F is going to be equal to Q times V cross B, but because V and B are perpendicular to each other, I and negative, this should be negative J in our coordinate system, not negative K. That should be negative J. Sorry about that. So, but I and negative J are 90 degrees to each other, so this is going to be QVB sine theta, which equals just QVB. Okay? And this reduces to 1.6 times 10 to the negative 19 coulombs times 4 times 10 to the 5th meters per second times 0.5 Teslas. Okay. And if I multiply this out, right, then I will get a value of, plugging this into my calculator, 1.6 times 10 to the negative 19 times 4 times 10 to the 5th times 0.5. Okay. So, the force on this proton is going to be 3.2 times 10 to the negative 14. Okay. And this is in newtons. Now, we can ask, gosh, that doesn't seem like a really large force. But remember that the force is acting on a proton, and a proton's mass is 1.67 times 10 to the negative 27. So the acceleration the proton experiences is huge. Injecting a single proton into a 0.5 Tesla magnetic field is immense. Okay, the acceleration the proton would feel is absolutely immense. Okay, and from the right-hand rule, if v is in the plus x direction, b is in the negative y direction, then this is going to be in the negative k direction. Okay, and that's just from the right-hand rule. And we can actually then work this out and make sure that this expression agrees with this, right? So if we do part B, right, so we're going to set up the matrix. Oops. Okay, so we don't have, we do have a velocity in the I direction. So this is going to be, let's label this as Vx. And V doesn't have any components in either the J or K directions. And the magnetic field has it in the negative J direction. So this is going to be negative B. Okay. And then it doesn't have any components in the other directions. So when I do the matrix, this is going to be 0 minus 0 times negative B in the I direction. I keep writing J. That's the I direction, minus Vx times 0 minus 0 in the J direction, plus Vx times negative B minus 0 in the K direction. Okay? And so the V cross B gives you the velocity in the x direction times the magnetic field in the negative k direction. Okay, I'm allowed to take this negative sign and apply it to the sign. So that way this just gives me the magnitude, and then the sign here gives me the direction. And that's exactly what we have here. Now, up here, we've already multiplied by the force, or by the charge to get the force. But this is just the V cross B part. So then the force is equal to Q V cross B. And we just showed that V cross B is equal to the velocity in the x direction times the field in the negative k direction. So we get QVB in the negative k direction, and that is exactly what we obtained here, QVB in the negative k direction. So we don't need to multiply all this out again. This is perfectly fine. But these results agree. Okay? So both results are consistent. Both definitions of the cross product work, the matrix definition, and then the magnitude of V and B times the sine of the angle between them. All right, so what are the units on the magnetic field, right? The units on the magnetic field are the Tesla, and this is the SI unit of magnetism. Okay, and you can actually kind of get a sense of what the unit of the Tesla is just from this equation. F is equal to QVB. Okay, now this is newtons, this is coulombs, this is meters per second, and this is Teslas. So if I solve this for B, B is equal to F over QV. Okay, so B is going to be equal to newtons over coulombs times meters per second. Okay, but if I rearrange things, newtons times coulombs per second times meters, then coulombs per second is current, so this is amps. So newtons per amp per meter, okay? Now that may not be a very intuitive unit, but it's force per unit current multiplied over a distance, okay? So this is a fundamental, or hints, I should say, at a fundamental property, and that is, as we'll see in the next videos, that the source of magnetism is current. And that appears in the units right here. Okay, so anytime you have a moving charge, anytime you have a charge in motion, you will have a current. Okay, so with that in mind, actually, you know what, we can break this down even a little bit further if we want to. Okay, so remember, newtons is kilograms times meters per second squared. So this turns out to be newtons per amp times meters, which is kilograms times meters per second squared over amps times meters. So my meters cancel out. And another way of thinking about magnetism, this may not be as informative as force and current and distance, but this is also the same thing as mass over current times time squared. Okay. But again, the bottom line still is that this one's probably the more useful. But the bottom line is that your source of current or your current source is where your magnetic field comes from. Okay, and this is a hint of what's to come. Okay, so it will turn out that not only are electric fields and magnetic fields related, and that magnetic fields are generated by current or moving charge, and of course charges carry electric fields, we'll find that there's an even deeper connection between the two when we get to electromagnetic waves and how those waves propagate through space. Okay, so with that, we will leave that here, and in the next video we will talk about the forces on current carrying wires and how to describe the magnetic field of systems using the Biot-Savart law. All right, we'll see you then.